And again, a picture of that terrestrial spectrum. This is the kind of absorption you might find in a conventional solar cell. This is what you might do if you had a multi-junction solar cell. You're basically absorbing the light from different parts of the spectrum. Now, there are two things that are important here. One is that you absorb the wavelengths of the light in the solar cell material of choice. So if you look at that blue cell, you want to absorb the blue light, but you want to let all the other light go through. Okay, so you don't want to impede that. Likewise for the green, then the yellow, then the red. Okay. In the end, what you get off the back is sort of waste heat into the cell. In concentrator photovoltaics, the game is very, very simple. The deal is that the optics for a concentrator are cheaper to manufacture than the cell itself. And so what you are betting on is that you can do lenses and reflectors and refractors much more cheaply than you can do a solar cell. Now, if you think about it, in some ways, that's a logical thought process. In fact, the predictions in the early days of concentrators were that they would be about a third the cost of a flat plate system. That has never been proven because there really wasn't enough push in the concentrating industry to drive them to much of a final product, and nothing with the kinds of production that you needed to drive down costs. The cells that go into these concentrators, and these are space cells, by the way, modified to be used as terrestrial concentrator cells, are kind of complicated affairs, as you can see there. They are semiconductors with tunnel junction interconnects, okay, and you've got to get it all right if you want your cell to work with high efficiency. There's even a new element. This is this lattice mismatched. These can be grown. If they're lattice matched, you can grow them in metal organic chemical vapor deposition process. If they are mismatched, meaning the lattice of one material is different from the lattice of the material under it, then you will have strains and dislocations that ensue in the final product. Now, there are tricks of the trade, folks, that are out there to ensure that you can do this. And in fact, people have been playing that game now for some time. The best cell is the gallium indium phosphide on gallium indium arsenide on germanium. This is a germanium substrate, a lot more expensive actually than a silicon substrate. And you see that two things about this. One is that the open circuit voltage is a lot higher than the other cells, and two, the efficiency is a lot larger. And if you go to these thin metamorphic structures, you could envision even more higher efficiencies. Now, there is a cost to all of this. If you go to the inverted metamorphic structures, you've got a lot more handling involved in producing the cell. So the question comes back to one of, can you make a complicated cell cheaply? And I would say the jury is still out on that. There are concentrator companies. There are a fair number of them. Some have been in business quite a long time, and in particular Ammonix and JS Crystal and Sol Focus. Others are new on the scene. This is an example of some of the concentrating systems that have been put up. Generally, they're done as grid integrated systems for utility companies. So you see, for example, here a large reflector. Here you've got a refractor. Here you've got a combination, in fact, of both reflection and refraction. And then you even have some that can be put on the roof. New companies, relatively new companies, in on the system. They have, and remember this is another key point with concentrators. You have to track the sun. Okay, so you've got a much more complicated installation. Not only that, you need direct sunlight. Wouldn't do you much good today, would it? So concentrators may not fare well. We'll let you know with the one in Cleveland how well they fare, in particular in the winter months. This is again more examples of the concentrating systems that are there. In theory now, the optics is simple. You know, it's making a mirror basically, or making a plastic lens, if you will, for the refractors. And they are now assembling these, and this is what one looks like from sole focus, which is a combination of reflecting and refracting. And there are other cell types to be complete. We've now got dye cells, meaning we have a material that absorbs the sunlight with a dye. Usually these are both a dye and titanium oxide as an electrode. If you look at their efficiencies, they are now up to about 11.1%. When they first were produced, the drawback was they were done with a liquid electrolyte. But there are now solid state versions of this. So these are the kinds of things that you will see. Also, they're very good in low light situations. So where you're finding them these days are in watches and other small consumer electronics. And of course, last but not least on the scene, but way down here at 5.5%, you have the organic cells. Now, organic cells have a whole new set of material problems that go with them. And it's just a relatively new technology. Part of the problem is that most polymers absorb in the ultraviolet, of which you get little of on the surface of the earth. So it's a matter, but chemists are wonderful things. They can break all those mirrored bonds and make new materials. And I believe that they will indeed get a polymer that absorbs in the visible region. But it isn't just the absorption that's a problem. It's that when you make an exciton in an organic cell, it doesn't live long and it doesn't go far. So you've got to make your junctions close, you've got to separate the charges quickly, and you've got to make the polymers conductive somehow. And so there are lots of games that are being played out there. And there is, last but not least, my favorite area, all of these wonderful new things. And if you look at theoretical efficiencies, those of you who should be in a thermodynamics class, this is a great place for you. Because if you do the thermodynamics of these systems, you can get these theoretical efficiencies for all of these different kinds of cells that are proposed. Now, the theory is a long way from the actual experimental product. Remember that. Well, let's just suppose for a moment that you could actually do it. Well, then you could envision this being quite dramatic in terms of reducing the cost. Wake up. These are what some of these cells look like. This is an intermediate band cell. There you go from a 31% theoretical maximum without that middle band to a 66% theoretical maximum for a single band intermediate band cell. You have other things you can do. You can use heat. You can use thermophotovoltaic conversion, where you're actually converting the very low energy photons into electricity.